Hi everyone, this is the explanation for my homework 2. Homework 2's task is to build some simple handwriting digit recognition using deep neural networks, abbreviated as DNN, on the MNIST dataset. So during the lecture, Professor used TensorFlow, but during my past year as a research assistant, I'm not so familiar with TensorFlow, so I switched to PyTorch for the implementation. And also, I compare some activation functions and the DNN architecture about like the trade-off between the network depths and widths, and compare the activation functions and learning rate, etc. Okay. And of course, as it is required, we import the libraries, the foreign library necessary in the homework requirement here, and also some PyTorch library for our implementation. And we also check that we do have a GPU to use. So you can just connect to T4 if you want to run this Colab notebook. And in block 2, we load the MNIST dataset and preprocess it. So MNIST dataset contains 70,000 grayscale images, which is 28 by 28 pixels of handwritten digits from 0 to 9. And the following code basically do read the dataset and do some data splitting into 60,000 training and 10,000 testing images. And we of course do some normalization to normalize the features that we are going to train our models. Okay, so this is quite basic steps, and this is our neural network architecture. So we define our number of layers and using the MN, which is the submodule in PyTorch. And at first you can see that we use the input is 784 features because the input images is 28 by 28. And the hidden layer is what we are going to try and see the differences between the differences across different configurations. And the output is 10 classes from digit 0 to digit 9. So the two modifiables is the hidden layers and the activation functions here. Okay, so the training and evaluations are just the training is just including some forward pass, loss calculation, and after calculating the loss, backpropagate the loss to update the weight in the neurons. Okay, and we also saved the best model in terms of the highest validation accuracy. And we also plot the training process using the accuracy metrics, record our loss, training loss, validation loss, and accuracies. The loss and accuracy on the training and validation datasets. Okay, this is a code. And finally, we visualize functions is for plotting the history, as mentioned before. So visualize has some benefits to diagnose any overfitting or monitoring whether our training will converge, etc. Okay. So our experimental configurations contains 8 different configurations, and you can see that the first one is comparing depth versus width. So we use 2 layers, and the second one is 5 layers. And the second setting is to compare different activation functions. One used hypertension, and the second one used leaky value. And we also compare the optimizer and learning rate. One uses SDG with momentum and use SGD as an optimizer. And the second one we use a higher learning rate set as 0.0.1. And finally, we compare the wide networks and narrow networks, which have a comparable number of trainable parameters. So we run our training code. I'm not going to run this. The time to run it took around 1 hour on T4 GPU provided by Colab. So the result analysis. Okay, let's see it. Where's the results? Gradual interface. You can see that the output shows the illustration of the training and validation loss and accuracy on the 8 high performance parameter setting, and also we draw some confusion matrix for the final result. So we can see in the output, you don't have to run it, basically just reproduce the same results. Okay. So what's the conclusion here? So we can see that the best test accuracy is the SGD with momentum, and the best validation accuracy is using wide networks. And the fastest training process is also SGD with momentum. Okay. And finally, we also show the results using these standalone block to train only the best performance configuration. The best for quick implementation. I only trained 10 epochs in list visualizations. So you can see that the final result is not so as good as it reported in the 30 epochs. It's like 7. Oh, it's not running now. So if you run only this block, you will be able to see the prediction by testing different handwriting here in the gradual interface here. Okay. So as mentioned before, highest test accuracy is SGD with momentum. So the key experiment findings here is what's really important is 5 layers test accuracy, 98, around 98 is a good performance, but not the best. Shallow is also around 98% at test accuracy, so it's surprisingly competitive with its deep neural network counterpart. So between the wide networks and narrow networks, we do see that wide networks, 2 wide layers, in this specific case, has a better test accuracy. Okay, it's not a general but we cannot draw the conclusion that white is better. So it is just a specific case that white networks performs better in this data set and configuration. Activation functions, and we can see that leaky value has the best among value and hypertangent, which had 98.25%. Optimizers SGD with momentum has the best overall task accuracy. And the training efficiency in terms of time on SGD with momentum can be trained with the fastest pace. Okay, and that's it. So basically, the task accuracy lies in between 97, 98, and the conclusion may not be generalized into all the data sets or architectures, but you can still try different configuration in the final block here, and to see the final result. The gradual interface are also provided here, and thank you for your attention.